Hello everybody, and welcome to section 2 on relative age. So, you go out into the field, you're hiking in a national park, you're doing something, and you come across something that looks like this. So, which do you think was laid down first, and which rock layer do you think is the oldest? So, more than likely, very likely, the oldest rocks are going to be on the bottom, the youngest rocks are going to be on the top. So something like this, our sequence for what happened is first was this layer, then the next one on top of it, and then the next layer, and then the next layer, moving up like that. Let's talk about sedimentary rocks. So you imagine you have a mountain, something big chunk of rock sticking up into the air, and it's subject to rain and snow and all the elements, everything from weather, and it's broken down into these tiny little pieces, and these roll down the mountain into rivers. They get broken into smaller and smaller and smaller particles until they finally get laid down somewhere. And after these get laid down and buried, they start to dehydrate as they sink further into the earth, and they start to compact into sedimentary rocks. Sedimentary rocks are made up of these different little grains, these different particles of sand or pebbles or even smaller things, little clays, sometimes chunks of other rocks in there. And these form in horizontal layers. Something like this. If you're driving by it, roadside geology, you could tell very high confidence that this is a sedimentary sequence here, that these are sedimentary rocks. On the other hand, you have igneous rocks. So igni, like ignite, these are born of fire formed with hot liquid magma or lava, cools and then hardens below the Earth's surface, in some cases cooling in a magma chamber, or spewing out as lava onto the Earth's surface. Something like this, which you might recognize, is the granite half dome at Yosemite National Park. This is an enormous igneous rock. You notice, unlike the other slide, you can't look at this and break it into layers. There's maybe a little bit of structure in this direction, but it certainly doesn't go through the whole thing. In fact, you can't really say that this is layered in any sense at all. This is a giant magma chamber which has cooled slowly over time and then kept its shape and been resilient as everything else moves around it. Now, this here is also an igneous rock. You might want to take a moment and try to figure out what location it might be that you guys are looking at here. So this in Flagstaff is actually in Arizona. We have a layer of lava that was laid down here. This black, thin, sort of runny stuff that came out and spread out over an area and then cooled and hardened. Also have our last class metamorphic rocks. So we might take one of the first rocks here, a sedimentary rock or an igneous rock, and we cook it. We expose it to really high heat or pressure, and we keep it that way. And something about the chemical composition, the internal structure of the rock changes. And just like with cooking, when you cook pasta or something, you don't melt the pasta, you don't burn it either. That's not really what's going on. You're changing the chemistry of it, but you haven't melted it. At no point did the pasta become liquid. Metamorphic rocks are cooked rocks. And you can look at these. Sometimes they do have a little bit of structure to them internally. We'll talk about this more in a later session. See that this little band here seems to go across it. And we didn't see that with what we were looking at before, the igneous rock, the big half dome. We call this a fabric to the rock. It's not exactly a layer that we see here, but there's definitely some sort of pattern to it. This is not totally random. Finally, sometimes we would go out and find what's called an unconformity. We'd find something which tells we, the geologist, or we, the interested person, that there is missing time represented in some body of rock. There might be, for example, something like this. So what happened here? Well, we have this body down here, which looks maybe like it is divided into these layers. So maybe we had these layers put down, and then something came along and folded it up. It pressed against it from both sides like this, and folded it into this shape that we see now. And then, for whatever reason, it was exposed to the surface and it was cut off. Maybe it was eroded, maybe it was just exposed to the elements for a long time. So we have this big horizontal cutoff, very bizarre little structure there. And then we see pretty normal looking rocks deposited on top of it. Well, this right here, where my mouse cursor is, this is our unconformity. We could look at this and be pretty certain that there is time missing here. It tells us that this is not continuous, this is not the whole story here that we're looking at. There's time missing. And something has to exist first before it can be cooked. And the reason I'm saying that will make sense here in a little bit. Sometimes we can look at a rock and see where it might have come into close contact with something really, really hot. For example, we can see this sort of pinkish tan rock here. And you might see that this stuff below it looks very similar. I might go ahead and say that these are a part of the same rock. But then this thing in the middle, this is a little jet of lava or magma, something hot that would have came through here. And on either side of it, you can see that it's actually changed the rocks that touched it. This is contact metamorphism. And what might have happened is this rock here was laid down, and then this hot magma was injected and traveled up through it under high pressure and then burst out onto the surface here. Okay. This is what we're going to use to form the basis of our rule set when it comes to solving certain problems. Now, using some of the rules and principles that we've talked about here, we can actually start to put in order what's going on in a frame like this. First, the first two numbers in the access code are 9, 1. So we see a series of horizontal layers here. These are going to be our sedimentary rocks. We see these a little bit more. You'll start to recognize right away that we have a sedimentary sequence for these four. And we also have this, A. And even if I didn't tell you anything about A, you could look and see these stars, our contact metamorphism, and be able to tell that A has intruded into these rocks here. We have contact metamorphism here for D, for C, and for B. So I could propose a sequence of events here based on those rules that we've talked about. First was B, here at the bottom is the oldest, then C, then D. But wait, how do we know that we didn't have B and then C and then A came up and part of it was on the surface and then D was put down and then E? Why couldn't it be that way? Contact metamorphism. So for D to have this metamorphism, it tells us that D was here first and then A intruded into it and cooked a little bit of D that it came into contact with. Now, what we don't know here is what happened with E and A. There's two sequences that are possible. We could have B and then C and then D and then E and then A comes up and intrudes here on these rocks and cooks a little bit of that at the edges. Or we could have had B, then C, then D, and then A, and then lastly E laid down on top. So there's actually two possible sequences of events here. That's going to be all for this first part of section 2. We'll have a part 2 coming next.